couple of minutes late, so we'll make sure that we have the 20 minutes for each speaker. So, all right. All right, so it's my pleasure to have Matteo Salvador. He's going to tell us about whole heart electromechanical simulations using latent neural ordinary differential equations. So, thanks so much. Take it away.
Thank you for the nice introduction and for the invitation to this workshop. It's a great pleasure, of course, to be here today. I will actually talk about a project that started back in 2022 when I was postdoc in Milan, even though now I'm a postdoc at Stanford in Alison Marsden's lab. And this project involved actually several institutions throughout Europe, Politecnico di Milano, King's College London, and the Medical University of Graz. And as Flavio said before, I'm going to present a computational pipeline that enables real-time four-chamber heart electromechanical simulations using latent neural ordinary differential equations. Before diving into the technical details, I just want to provide a quick introduction about tools and needs that we are currently having in computational cardiology, broadly speaking. Starting from the left, nowadays we can certainly leverage several mathematical and numerical models that are multi-scale and multi-physics, and we can run very sophisticated, fully coupled electromechanical fluid simulations throughout the cardiovascular system via high-performance computing. But luckily enough, thanks to the advent of artificial intelligence-based methods, mostly driven by scientific machine learning in this field, we can nowadays build surrogate models that encode the temporal or the spatio-temporal dynamics behind the complex system of PDEs and ODEs. And we can, once we have these accurate and efficient surrogate models at our disposal, we can perform several tasks such as global sensitivity analysis, robust parameter estimation with forward and inverse associative quantification in very reasonable time frames and by using a very small amount of computational resources. All of that, by properly blending physics-based knowledge with data-driven methods, contribute to model personalization and digital twinning, in which we can envision in the future a continuous bidirectional interaction between clinical data and the mathematical models. We will have computational pipelines that support the decision-making process in the clinic and allows for personalized treatment and surgical planning. In the computational pipeline that I'm going to present, we have a little bit all of that. In particular, starting from top left, what we did was to run in a patient-specific scenario a huge amount of 3D, 0D fully coupled electromechanical fluid simulations, while spanning a huge parameter space, multi-physics and multi-scale. We collected the pressure volume loops in atria and ventricles coming from these simulations, and we encoded their dynamics for pressures and volume over time by using latent neural ODEs, and I'm going to dig into that later on, while spanning the parameterized time-dependent PD couple system behind that. And once we have this accurate and efficient surrogate model, we can perform GSA and parameter estimation with QQ in very reasonable time frames. And once we have the calibrated model parameters, we can feed them back potentially into the 3D 0D solver again, run a final set of comprehensive simulations where we can extract all the quantities we might be interested in. Just a few details about the electromechanical model. All the simulations run using CARP. We consider, from the Medical University of Graz, we consider a patient-specific geometry challenging case, 78 years old female heart failure patient with atrial fibrillation. We map fibers from ex vivo DT MRI using universal electrical coordinates for the atria, and we rely on standard rule-based methods for ventricles. For electrophysiology, we run the equivalent equation with the Kurte-Marshall-Miller-Stratton model for the atria and the total model for ventricles. We calibrate the LAM model in different manners for atria and ventricles for active mechanics, and we consider a standard transversal isotropic Guccioni model for passive mechanics. And finally, we perform the coupling with the 0D LAM parameter model for the circulation system using CircAdapt. Here you can see a list of all the 43 model parameters that we encoded in the surrogate model, and this list actually comes from a very comprehensive sensitivity analysis that Marina Strocchi did, and she's going to talk about that tomorrow, so I'm not going to dig into much into the details of how these parameters have been extracted. But the idea is that you have a little bit of everything encompassing cardiac electrophysiology, active and passive mechanics, and cardiovascular hemodynamics. And on the left, you can see an example of 3D cardiac electromechanical simulation, and I'm pretty confident that given the recent advances in neural operators, we will be able to encode these multi-physics and multi-scale spatio-temporal dynamics into neural networks pretty soon. But for the time being, we're focusing on the collection of pressure volume loops coming from these simulations for atrial ventricles, and we use latent NeuroNODEs to build our surrogate model. The idea is that we have a very simple and compact, feed-forward, fully connected neural network, ANN, which acts as the right-hand side of a system of ODEs that we want to build from scratch, where the vector z of t contains some physical variables of interest, such as the pressures and volumes in time, plus some latent outputs which allow to enhance the neural dynamics and to stretch the trajectories that we're actually getting. This artificial neural network receives as input the vector z of t itself. We have a couple of positional embeddings encoding the periodicity in sinus rhythm with a certain cardiac cycle THB, properly rescaled by the atrioventricular delay at the numerator, which is an important parameter for cardiac function. And theta is the vector of 43 model parameters I was mentioning before. W encodes weights and biases of the neural network. We perform a keyfold cross-validation on 400 3D0D numerical simulation spanning 43 model parameters. And as you can clearly see here, there is a kind of curse of dimensionality issue because we have a small amount of simulations for the hyperparameter space we are covering. But thanks to the physics informed the nature of this scientific machine learning tool, plus this loss function that we are leveraging on the left, we can actually get really good generalization properties. And in general, in scientific computing, we cannot really run an arbitrary amount of simulations, so we want to make sure that we can generalize even if the data set is not big enough. And going to the loss function, we do not simply minimize the normalized root mean square error between predictions and observations in the physical space, but we also weakly penalize the time derivative, the maximum and minimum values attained by the neural network with respect to the observations. We also enforce periodicity in the latent space, and we are always looking for expressive, interpretable, and parsimonious architectures. So we are weakly regularizing in the L2 sense weights and biases. We perform automatic hyperparameter tuning using a Bayesian optimizer, and we employ an asynchronous successive Alfio scheduler to drop out from configurations that are not promising since the very beginning of training. And from what you can see here, we have the ranges that we consider for the tuning process, plus the final configuration we ended up with. And with a very compact neural network with just 3D layers and 30 neurons per layer, we can capture the dynamics in faster real-time simulations very well. Here you can see the overlap between the 3D0D model and the artificial neural network-based model for pressures and volumes in 5 additional simulations that are comprising of the testing set. And of course, in this case, we didn't consider a very huge testing set, so we tried to push even forward the capability of the method and see, and by fixing the optimal architecture, we try to consider different splittings between training and testing. And even if we consider something like 265 and 40, and of course the normalized root mean square error are slightly increasing, we still get excellent generalization properties thanks to the intrinsic nature of this scientific machine learning tool. So once we are confident about the capabilities of the reduced order model, we started by running a global sensitivity analysis. Here you can see the total effects of all indices, where we capture first order and higher order interactions between model parameters, electromechanical model parameters, which are the different rows of the table, and different quantities of interest, QIs, extracted from the pressure volume loops. And what you can see looking at this area at the bottom is that the systemic and pulmonary resistance together with the atrioventricular delay have a major role in determining all the outputs of the pressure volume loops. And then most of model parameters are actually compartmentalized in the sense that the parameters belonging to the ventricular electromechanics part are mostly affecting the ventricular function, and similarly for the atria. But there are some important exceptions, in particular this area of the table right here, in which there are some cellular parameters of the Tororland model for the ventricles that are impacting the atrial function. And unraveling this type of mechanisms wouldn't be possible if you don't run this type of global sensitivity analysis, especially in such a complex, fully coupled and nonlinear model. And it can be useful potentially also for drug development and to design pharmaceutical targets in the long run. And once we are confident about which parameters we can actually identify at the cell and at the organ scale throughout electromechanical fluid simulations via GSA, we perform 4 different in silico test cases with increasing level of complexity, where we provide some time-dependent quantities of interest, volumes or pressures over time, coming from atria and ventricles, and we want to estimate many more model parameters with respect to the quantities that we provide, because of course, given the fact that we don't have point-wise values, but we are actually living in a functional space, we can actually do that. And we start by performing maximum posterior estimation to find an initial guess of model parameters, followed by a Hamiltonian Monte Carlo to get the whole posterior distribution. Here we are in a full in silico scenario where we want to estimate quantities from the 5 simulations in the testing set that you saw before. So we have the ground truth. And in each subfigure, you see that the black dot is always contained within the 95% credibility region of the posterior distribution. Here I'm just showing some bidimensional cuts of the posterior distribution. And thanks to Bayesian statistics, we can capture cross-correlations among model parameters, even if they belong to different compartments. For instance, here you see that the systemic resistance is negatively correlated with calcium parameters of the Thoroughland model. And we also capture multimodality in this very complex model. So we allow for multiple areas with different level of uncertainty that we can explore during the tuning phase. And in this pipeline, we can also encode not only the surrogate modeling error that we introduced by switching from the 3D 0D solver to the neural network, but also potential some measurement errors, and there are more details in these references in how we actually do that. To conclude, what we did was to develop a quite comprehensive surrogate model of cardiac electromechanics and cardiovascular hemodynamics by leveraging latent LNODEs. We have a very lightweight neural network which enables faster real-time numerical simulations, and the overall speed up that we can provide with this pipeline is pretty massive. If you look at the table at the top, you see that running a single simulation with a 3D 0D model on more than 500 cores still requires 6-7 hours of computation. And if we would have used the 3D 0D model for GSA and parameter estimation with UQ, by using high-performance computing, it would have taken for a single instance 5 centuries of computations. On the other hand, if we are willing to pay the price offline to generate the training and testing set, which even nowadays poses an incredible technological challenge given the complexity of the model, then we can train the use of the model, perform GSA and parameter estimation with UQ on just 1 core in a few hours. In terms of future developments, what we want definitely to do is to have a model that is not necessarily geometry specific, so a surrogate model that is able to generalize across multiple hearts, different anatomies and different pathological conditions, so that we don't need to retrain it on a patient-specific basis. Before concluding, I just want to mention a few references that I think might be of interest. So the first one is the paper on MPGA digital medicine I just described. And then I just want to briefly mention a couple of projects from Alison Marsden's lab at Stanford, where I'm actually working, where the focus is mostly on pediatrics and congenital heart disease, broadly speaking. So I've been working on developing some digital twinning pipeline for congenital heart defects, in particular hypoplastic left heart syndrome. And along the way, given the, of course, big need in creating surrogate modeling techniques, we developed a new method, a new neural operator called branched neural maps, which is extremely compact and lightweight to train and to run inference with. It is discretization invariant and allows to map temporal, spatial, and time-spatial processes coming from a couple system of PDEs and ODEs. And the last reference I want to mention is this paper on natural communications with my colleagues from Milan, where we develop a new scientific machine learning tool called Latent Dynamics Networks to actually embed spatial temporal processes coming from arbitrary sets of PDEs and ODEs while spanning initial conditions, boundary conditions, physics-based model parameters, and so on and so forth. And this can be useful, of course, to create the next generation of surrogate models in computational cardiology, hopefully, and also in other engineering applications. The first QR code on the left contains the code for the MPJ digital medicine work to train latent LNODEs, run GSA and parameter estimation with UQ. The QR code at the center contains the code for the digital twinning pipeline for congenital heart disease plus branch neural maps, and the QR code on the right contains the code to train and run inference for latent dynamics networks, and everything has been released under MIT license. And that's all from my side. Thank you very much for your attention. I will be happy to take all your questions.
Thank you, Matteo. Very nice. So we have 5 minutes for questions.
Yeah, brilliant, thank you. So how sensitive are the results of the sensitivity analysis to the high parameters of the loss function?
Okay, so we try to make sure, so the results of the sensitivity analysis are sensitive to the ranges that we consider for the parameters of the physics-based model. So if you train the neural network well enough with optimized hyperparameters, they shouldn't be sensitive to the loss function that you actually get, especially if you get good generalization errors like this, matching almost perfectly the traces of the full order model. Thanks.
Any other questions?
Gary Myers, Nottingham. So we've found neural ODEs very good if you can cover the space of the training so that they've seen everything they're ever going to need to predict. But if there's any gaps in the training data, then it just kind of can go a bit crazy because they've just got no training points around there. Have you found anything like that, or is there some scenarios that you know you won't be able to predict?
Yeah, so I'm pretty sure that if we are going in extrapolation in the parameter, if we're going out of distribution in the physical parameter space, we definitely cannot do that, but we make sure to constrain the hypercube in order to have prediction and observations for GSA and also parameter estimation within that. I'm sure that going a little bit further, for instance, using liquid neural networks or from MIT, other tools like neural circuit policies or even transformers, we maybe fill the gap in doing that. But I think that the problem is that in this case, you really need lots of training data to go out of distribution.
Yeah, there are PV loop catheters now clinically available.
Yes, there are. We didn't use them in this project, but the idea is that we put some kind of the bed of the parameter estimation pipeline where we tested everything in silico, giving pressure volume loops coming from simulations and the self-organ scale parameters that we actually have from the physics-based model. But the idea in the future would be to not give just numerical simulations at targets, but directly pressure volume loops coming from catheter or from CT.
Yeah, no, we use them a lot, and I think the opportunity is to, the way we use them is to then vary the hemodynamics by increasing inotrope or giving fluid bolus or a variety of factors that you could actually validate your model by using pressure volume movement machines, the electrophysiologic parameters, cardiac, bradycardic, whatever you wanted, and understand that. So I think that's going to be a super important validation opportunity here. There's a lot of unknowns.
Perfect. Yeah, I totally agree with you. Thank you so much.
All right. Let's thank Matteo one more time. Oh, there's okay. No, that's okay. We can.
How do you choose the range of variation for the model parameters?
Okay, so some of them are taken from literature, considering the cohort of heart failure patient with defibrillation that we investigated. Some of them are tuned from the clinical data that we have at our disposal. So some parameters for electrophysiology, for instance, are tuned so that we can match the QRS duration from the ECG of the patient that we have. Then we also have a penalty method at the boundary to constrain the movement of the displacement at the epicardium following the dynamic CT. So some of them are constrained thanks to the imaging or invasive data that we have on these patients. Some of them are coming from literature. Thanks.
All right, any other questions? Let's thank Matteo.